Hello, today is October 14th and this is Cal 1 online lecture number 2 of this week. First of all, I have to correct something that I did in the previous video. It's about this table. So I did some, I would say, silly mistake, so let me address that. So last time I was working on this differentiation of arcsine. So I have this arcsine, arcsine of kx, and then I perform this differentiation on this function, and after some work I got to this conclusion. In the end, I have this equation 1 over k arcsine of kx plus c. After some integration, I have this constant c from the indefinite integration, and this is equal to the integration of 1 over square root of 1 minus k square x square. This is what I got in the end. And then somehow I told you that this 1 over square root of 1 minus k square x square is the antiderivative. That was completely wrong. That is the other way around of what is supposed to be. I integrate this and I get this, which means that this is the antiderivative of the function inside the integration of this fx. So what we see on the left hand side, this is f, big F of x. So this is what is supposed to be the correct explanation for this result we got last time. All right, so don't get it wrong like don't get it wrong like I did in the last lecture. Okay, now after that we can move on to the new topic of today. Today it's about the integration again, but we are going to use the integration to find the area between two curves, or you can say two functions. So let's move to this slide. Okay, we have done that. Now let's move to this one. This is about definite integration as the area between two curves. So this is going to be related to definite integration. So let's bring that back here. What we learned about definite integration, it's about integrating certain function, right? But this is definite. So we have starting point and the end point of this integration, starting at x equal to a and ends at x equal to b. And from the fundamental theorem of calculus number 2, we know that the result of this is the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay, this is from the, well, I can make a note here. This is fundamental theorem number 2. All right, and we didn't learn just this. We also learned about the physical meaning of definite integration. We also know that this definite integration also corresponds to the area under the graph fx from starting point A to the end point B. So let's make a note here in terms of physical meaning. So this is area under graph fx, or you can say under the function as well, but in the end you plot the function, it becomes curve. The area under fx from A to B. So with this you can imagine this kind of graph. Oh, that's a bad y-axis. Let me fix that. Okay, we have this y-axis and we have this x-axis. Now we have this graph. Let's say this is fx. All right, this is y-axis, this is x-axis. Right, and this is fx. And when it comes to definite integration, so we have this starting point at a, x equal to a, and end point at x equal to b. And this definite integration is the area under this graph. Right. Okay, so let's put this into some formula here. This a is going to be equal to integration of fx with respect to x. Right now we are working on x variable, so of course we have to put dx there, and this is integration from a to b. Now we have seen this, but what we don't know is that there is something hidden inside this definite integration, because actually there is this extra term following fx. So let me write that down. So instead of having integration from a to b and just fx, we actually have this 0. Alright? If you compare them, it's the same thing, right? Fx and fx minus 0. But why do I put 0 there? This is because I want this to correspond to the height of rectangle in Riemann sum. Sorry for the space here. This Riemann sum. So when it comes to this rectangles in Riemann sums, we are talking about these small rectangles that looks like that. And we don't just have one of them, we have many and many of them. Alright? So as you can see here, the height of this rectangle is the function value right here, and it actually minus with the 0 value right here. So the height here, as you can see, the height of this rectangle is f of x. Okay, now I want to transform this expression that we have to a little bit different, a little bit further than this. So what if I changed the 0 to something else? Integration from a to b just the same, and fx just the same, but then I want to change this 0 to g of x. All of a sudden this becomes another function. You might ask, how can you do that? This is different things. So let's take a look here. To go from 0 to here, this is possible if we set gx equal to 0. Gx equal to 0, this is a function, right? And what it means is that this function is always equal to 0. In other words, this is the x-axis. Okay, so we transition from 0 to gx by setting this gx equal to 0. So what we see right here is that we see one function at the top, or you can say upper function, fx. Fx is right here. And then we have this gx right here. Notice this. This is one function at the top, fx, and one function at the bottom, or you can say lower function, gx. Now, take a look at this height of this rectangle. Now, it's going to be a little bit different from before. Before it's just fx, but now this height of this rectangle becomes fx minus gx. So this, we are talking about this rectangle, right? So instead of looking at the base as just 0, now we look at this base as gx. Okay. One thing I would like to talk about here is that when it comes to fx, is the fx minus gx here. I mentioned that this term is the height of the rectangle in Riemann sum. The height has to be positive. So let's write that down. Fx minus gx the height of this rectangle must be positive. So we switch around, it says that we can see that fx has to be greater than gx. Now, once we get to here, let's put a meaning to this inequality. This inequality tells us that fx has to be the curve at the upper part, at the top, and gx has to be the curve at the base. Fx has to be above right here at the top, right here, and gx has to be lower at the base, so that when it comes to fx minus gx, it becomes positive. So let's put meaning here. Fx is upper function and gx should be lower function. In other words, if you want to use this expression, area coming from the integration of fx minus gx, fx has to be above gx. All right, so this is very important. And the keyword for fx is the upper function. The keyword for gx is lower function. Now, let's take a look at the formula that we have here. Here we are going to have this formula a equal to integration of fx minus gx dx, starting from a to b, just the same. Before we have this physical meaning as the area under fx from a to b. But then I want you to make a note here. The meaning of this is a little bit different from above there. This becomes the area between fx and gx. In this case, we have relation between two functions, fx and gx. All right, and of course, this has to be from one end to the other end, from a to b. I want you to take a look at this. This is the main difference. This is about having gx right here, and up here is just the area under fx. But in the end, it has the same origin. It comes from the same place. Now we have this formula to use. So let's use that to solve some examples. Okay. All right. Let's move to the next slide. Oh, before I move to the examples, let me talk a little bit about this graph. So I mentioned before that fx, this is very important, has to be above gx, which means that if you want to use that formula, fx is going to be upper function, upper, and gx is lower function. This is very important, because if you pick this order wrong, in the end, you might get the result that has a wrong sign. All right, plus and minus sign, very important. How do we know which one is above, which one is lower? You have to plot them. So the best way to solve the area between two curves, the first thing you should do is you plot them. For example, in this case, if you have fx, just plot them. Let's imagine that we have this fx up here, this function up here, and then another function down here. From the look of this, from the shape that you see in the graph, you can tell that this blue line is at the top of this region. So we are going to call this fx. But then you see red line at the base of this region. You are going to call this red line gx. Alright, and if you want to look further into the Riemann sum, that's going to look like that. This small rectangle, and as you can see, the height of this rectangle is fx minus gx. That's why we need fx to be above gx. Okay, now that you see the shape of this and how we see the relation between fx and gx, let's move to the examples. All right, now take a look at this example. We want to find the area of the region enclosed by one parabola and one straight line. So the first curve is this, y equal to 2 minus x squared. And the other line is 1 equal to x. We don't know what this looks like, this region looks like. So if we don't know the shape, then we can't determine which one is the upper function and which one is the lower function. The first thing we need to do is to plot these two curves on the graph. So let's do that. So let's say we have this x-axis. All right. Okay. Okay, this is better. We have y-axis right here and x-axis right there. Now, let's plot 2 minus x squared. Some of you might look at this and don't know where to go. I want you to look at this from part by part. When you look at the whole thing, you don't know what it looks like, but if you look at this, just minus x squared, you know right away this is something about parabola, right? But it's going to be parabola upside down because we have this minus sign. So we expect an upside down parabola to appear in this graph. But then we have this 2. It means that this is an upside down parabola shifted up 2 units. So shifted up 2 units, let's say here, and it's going to be upside down parabola. So let's put that in the graph. Maybe something like this. We have 1 and 2. Okay, so that is the first curve. Now the second curve, this one is easy. Y equal to x. So we can just plot it. Y equal to x straight line like that. Okay, so with these two lines, you start to see a region that is enclosed by them. And you can see that this is the region we are looking for between the parabola and the straight line. Now, the next thing we need to do is to determine which one is the upper function fx. Fx equal to what? And gx equal to what? You can't just assign fx to just any of them. There is an order that we need to find out because we need to put fx for the upper function and gx for the lower function. Okay, now take a look at this. Upper function, look at this region. You can tell that the upper part of this region is this, right? Is at the top of this region. So you know right away that this line is fx. And this line is the upside down parabola. So fx has to be equal to 2 minus x squared. What about the base or the lower function? It's right here. You can see that from the whole geometry of this shape, this is gx at the base. So here gx equal to, well, equal to x. Once you have this region, I want you to imagine small rectangle that along the way in the Riemann sum, these small rectangle right? Well, I don't want to continue with that. It's getting messy, but you get the idea, because definite integration comes from all these small rectangles combined together. So we have this fx and gx ready, which means that we can use the formula from what we proved earlier on the previous slide. So the area between fx and gx, it's going to be the integration of the first function, the upper function, fx minus gx dx. Once again, upper and lower. Okay, now something is missing, and it's right here. It's missing starting point and the end point of this integration. Does it mean that this problem forgets to tell us? Is it a mistake from the problem? It turns out that it's not. It's not a mistake. The endpoints are given to us indirectly, even though it doesn't say in the problem itself when to start and where to stop. We can see that in the shape from the plot. We have a starting point when two lines intersect each other, and it stops at the point where they intersect once again. So our job here is to find out where this is and where that is. How to find that? We are talking about intersection of two lines, right? So intersection of fx and gx. How can we find that? We can just balance the equation. The first curve is 2 minus x squared. The other equation is x. So we can move things around, and we have x squared plus x minus 2 equal to 0. Do some factorization. We have x plus 2, x minus 2, x minus 1 equal to 0. Solving this, you know, this equation is true when x equal to 1 and minus 2. So the first point right here happens at x equal to minus 2. And the next point of the intersection happens at x equal to 1. So you know where it starts. Starts at minus 2 and ends at 1. So right here, even though you don't see in the problem where to start and where to stop, you have to plot it, and then you know where those points are. Right? So let's continue with this integration. Integration of from minus 2 to 1. Fx right here is 2 minus x squared. Minus gx is this, x. And we integrate this with respect to x. After this, it's going to be not too hard for all of you because we have done this before. Just regular integration. 2 becomes 2x. Minus x squared becomes minus x cubed divided by 3 to cancel the 3 that is going to come down. And then x here minus x squared over 2, and we have to evaluate this at two values, minus 2 and 1. So 1 goes in, this becomes 2 minus 1 over 3 minus 1 over 2. Then minus 2 goes in. This becomes minus 4. This becomes plus 8 over 3. It becomes plus because it cancels with the minus sign from 2. And minus 4 over 2 here, and the result of this these numbers is going to be equal to, well, let me look up, 4.5. 4.5 as the final answer. You can check the numbers again, but I think I got it right. 4.5. Okay, so this is how it's done. how to use this formula to find the area between fx and gx. The most important point is that you need to know which one is the upper line and which is the lower line, so that you know how to assign fx and gx. Okay? Alright. So this looks quite easy, right? Nothing to get confused about, but then it turns out to be a little bit more complicated than we expect. So let's take a look at how it can get interesting when it comes to this formula. Now let's take a look at example 2. In terms of the question itself, it's quite similar to what we see before. So let's take a look here. We want to find the area between of the region enclosed by, so we see the first curve here, parabola y equal to square root of x. That is the first curve. And then we have the line here, y equal to x minus 2. That's a straight line. And then we have x-axis. The first thing we notice here is that, hey, we have 3 curves, not just 2 like before. So we have 3 curves to worry about. And of course, we have to worry about fx and gx, which one is upper and which one is lower. So in order to find out about that, always plot it. Okay. Now we have this y-axis and x-axis. Let's plot the first one, y equal to square root of x. This is going to be equal to, it's sort of like a parabola on the side. Okay, so and y has to be positive, so we have this for the first curve right here. Parabola on the side and y has to be positive only. Okay, so let me assign the label here, y and x. So that is first curve, y equal to square root of x. Now second curve, or I should say line, y equal to x minus 2. This is a straight line with a slope of 1, intersects y-axis at minus 2. So we have this minus 2 right here. So it's going to be this. All right. Okay, this is good enough. Okay, now this is the second line, and the last one is the x-axis, and it's going to be this whole line here, x-axis. Once we have drawn the curves, then we have to determine the region enclosed by them. By the look of this, I want you to see this. I want you to be able to figure out where the region is. First line is this. First line is right here, second line right there, and the last line is there. Now, once you combine them, you can see that this is the region trapped by the 3 lines. And we want to find the area of this. Now, we want to use the formula that we have before. So the formula that we had before is this. The area equal to integration of the starting point A and ends at B, and then we need to know the upper function and the lower function, dx. If we want to use this, we need to assign fx to upper function and gx to lower. Now, let's take a look at the shape of this region. We need to determine the upper and lower lines. So looking at this, we know this is the upper curve. So we know that up here, this is fx. Now, what about the lower curve? Let's take a look here. At this point, this is lower curve, and this is x-axis. But then, after this point, the lower curve, or the lower line, is this. Right? It's no longer x-axis, it's the the straight line x minus 2. So this means that in this case we have two lower curves, g1x right here for the first part and g2x right there for the second part. So in order to find the area of this region, we have to split the region into two parts, right in the middle. Okay, now the next thing we need to find out is about this change of one section to the other. So this intersection of x-axis is equal to 2. How do I know? I solve this and set y to 0. Y equal to x minus 2 and 0 equal to x minus 2. So I know this happens when x equal to 2. Alright, so in this case, let me work on this. Instead of integration all the way through from, well, the next thing, there is another thing you need to know. What about this point? Well, sorry, I skip about that. When does this happen? At this point, we don't know yet, but the starting point, we know it's going to start at 0, right? So we know A is going to be equal to 0, but we don't know about B. So let's find out about that, about this point. So B happens when this curve, square root of x, intersect with the line x minus 2. So we have to solve this. So this becomes, let's square both sides, x, this x squared minus 4x plus 4. Move things around, you have x squared minus 5x plus 4 equal to 0. Factorization, x minus 4, x minus 1 equal to 0. And you can see that this is true. This equation is true when x equal to 1 and 4. And as you can see, this point has to be greater than 2, right? Because right here, this is 2. So this point has to be greater than 2. So it's going to be this 4 value. So the intersection right here happens at x equal to 4. So in the end, this is supposed to be 4. But now we are back to g1x and g2x. We know that we have to consider both of them. So instead of integrating all the way through from 0 to 4, we have to split them. The first section starts from 0 to 2. So we are talking about this section, 0 to 2. Upper function is the square root of x. Well, what about at this point? I'm gonna put fx for now. Minus the lower function at this point is g1x, which is the x-axis. Now, the second section starts from 2 to 4, this region, starting at 2 and ends at 4. Upper curve, same fx, but the lower curve is different. This is g2x. Alright, so to get this correctly, you have to split the integration. Now, after this, you can just perform the integration normally. 0 to 2, upper function, square root of x, lower function, x-axis. What is x-axis? This is y equal to 0 dx. Okay, and the other part is from 2 to 4. And we have the upper function, square root of x, minus the lower part is the g2x, that is the straight line, so that is x minus 2 dx. So let's integrate this. Let's integrate x to the power of 1 over 2. So this is going to become x to the power of 3 over 2, and we have to divide 3 over 2 to this term. So this becomes 2 over 3, evaluated at 0 and 2. Minus, let's integrate what's inside here. Square root of x, this becomes x to the power of 3 over 2, same as what we got before, 2 over 3. Minus x becomes minus x squared over 2. Plus 2 becomes plus 2x. And we evaluate this at two values, 2 and 4. Alright, and let's work on this. The front part, you are going to get 4 square root of 2 over 3. Now the second part is going to be, oh sorry, there is one mistake here. Look at this. This is supposed to be added together, not subtract, because we add the area of the two of them. So this is plus, change that. So this is plus. Alright, now 4 goes in, so we have this 16 over 3. And we have minus 8, 4 goes in, becomes 8 right here. And minus 2 goes in, we have 4 square root of 2 over 3 minus 4 over 2 and plus 4. Alright, and after you combine them all, it's going to come out to be equal to 10 over 3 as the final answer. In this example, what you need to be aware of is that sometimes the lower function, this gx, has to be split, because sometimes we have two sections of lower function. In this case, one section is the x-axis and the other section is the straight line. That's why you have to split the integration based on the lower function. That's why it's important to plot the region. That's how you know which one is the lower and which one is the upper. Without plotting, you don't know anything. Alright? Okay, now we are going to move on to, well, same example, but we are going to solve this example differently. So let's take a look at how this example can be solved in a different way. Alright, but expect the final answer to come out to be 10 over 3, just like what we did before. Okay, so with this, we are going to start with the same step by plotting the graph. Have the same thing, you have this. Okay, let me add this y-axis to down here, and then we have parabola on the side. It's going to look like that, and then we have this straight line intersects y-axis at y equal to minus 2. Okay, and then we have x-axis, so still the same region. This. How do we solve this differently? But before that, let me put some important numbers. 0, 2, and 4. Now, let me ask you, what about this value? What is this value? To know this, you just plug 4 into the equation, either this or that, and you know this is 2. Okay? Now, we are going to use another approach to solve for the area of this region. This approach is different in the way that we would integrate y variable instead. So that is the key word. What does it mean, integrate y variable? I want you to take a look at what we did before. What we did before here, which looks quite messy, we integrate what variable? X variable. So let's make a note here that what we did right here is the integration of the x variable. Integration of x variable. So when it comes to integration of x variable, it's associated with the Riemann sum in this shape, right? The height of this rectangle is fx. Okay, let me change color. The height of this rectangle is fx minus gx. So that is the concept that we follow in order to use this formula. But now, in this same example, we are going to work on y variable instead. So instead of having this rectangle vertically like before, right now it's going to be a little bit different. It's going to be horizontal instead of being vertical. So let's take a look here. Okay, the region looks just the same as before, but this time around we are going to work on y variable. So which means we have to look at things on the side. So the rectangle that we had before, it's going to become like this. Okay? The height of this rectangle is going to be the change of y variable. Before, the width of this rectangle is dx, x variable, and the height is the fx minus gx. But now it's different. The height become dy. And what about the width of this rectangle? It's going to be the distance between the two lines. All right, so let me put this right here. I'm going to define this line on the right hand side as fy. Focus on the word right hand side. And this on the left hand side is going to be gy. If we want to find the width of this rectangle, it has to be positive, right? So it has to be the higher value of x, which is fy, minus the lower value of x, gy. So the width of this rectangle is going to be fy minus gy. So let us modify the formula that we had before. Now the area, same thing as we want. Area between, in this case, instead of fx and gx, it becomes fy and gy. We work on different variable. All right, it's going to be equal to the integration of the add up of all these rectangles. So it has to be the area of this rectangle, which is the width of this rectangle, fy minus gy, coming from here, times the height of this rectangle, that is dy. Now we have to integrate over a certain range. So this range is going to be on the y variable. So let's take a look at the y variable for the range of this region. You can see that y variable starts from right here and ends there. All right, so here we have starting point for y variable, c, and ends at d. Okay. Make a note that c right here is y value and d right here is y value. Different from what we did before. A and b here is x value. Now we work on y variable. Okay, now we have this formula ready, but how to use it? So let's find out. The first thing is to find out about which line of this is fy and which line of this is gy. As I told you before, fy right here has to be on the left hand side. Oh, sorry, on the right hand side. As you can see, it's on the right. So just like what you see here, it's on the right hand side. and this on the right. gy, what about gy? Gy has to be on the left hand side of this region. So this is on the left, on the left. Okay, now that we know this, we just need to look at the shape of the region and determine the left and the right. You can see this is on the right, which means that this line corresponds to the right hand side. That is the straight line. This is the right, the right boundary, and this is on the left hand side. But don't forget that in order to put it in here, it has to be expressed as the function of y. But what you see in the problem, that is the function of x. So we have to do some adjusting. So from y equal to square root of x, we have to change this to be a function of y. So this becomes x equal to y squared. All right, and the other one is y equal to x minus 2. Switch things around to move x to be alone on the left hand side. You have y plus 2. All right, and this straight line, the one on the right hand side, this is fy. This parabola on the side is on the left, so this is g of y. Now we know fy and gy. What about c and d? Let's take a look at the shape. C is the y value of the starting point, that is 0. What about d? That is the endpoint of y variable, 2 right here. So this is different from before. Before we look at this 4 value, but right now we work on y variable. We have to look at the end of the range in the y-axis, so that is 2. So this equal to 0 and this equal to 2. Now let's continue. 0 and 2, that is y variable. What about fy? Fy, we know it's this, y plus 2, minus gy is this gy, y squared dy. So at this point you might ask me, why do we have to go through all this trouble? This is so many things to do. Let me ask you something. In this case, how many right curve do we have? You can look at this on this region. We only have the one right boundary right here. Over the whole region, this line is always the right curve, right? And then over the whole region, this parabola on the side is always on the left hand side, right? This one is always on the left and this one is always on the right, which means that we don't have to split the integration. Before, the lower function, first part is this and the second part is that. Upper function all the way the same. But in this case, we don't have to worry about that because one line is always on the right and one line is always on the left. So we don't have to worry about splitting anything here. So we just continue with this integration. Equal to y squared over 2 plus 2y minus y cubed over 3. And all we need to do right now is to evaluate this at y equal to 0 and 2. So this is equal to 4 over 2 plus 4 minus 8 over 3. And in the end, you have this 10 over 3 as the final answer. Same as what we got before. So it's up to you. You can choose to work on x variable like this. and just split the area into two parts and just work two integrations. Or you can switch to y variable based on the shape of the graph. Looking at this, you know, hey, this is going to be easier because we don't have to split it. One is always on the right, one is always on the left. All we need to do is just to switch from from x variable to y variable. The main thing that we need to do is just this switching. Switch from fx to fy and gx to gy, right? And in the end, you just need to work on this one integration. To me, I think this is faster because all we need is just switching the equation, and then the integration is simpler here. What takes time is this integration. That takes a lot of time to put all the numbers in and then add them together. But here it's just one integration, and I think it's more convenient and faster to execute. Okay, but up to you. In this case, well, in some cases, in some problems, only one method works. So it depends on the shape of the region. So you have to look out for that. Always plot the graph and you know what to do. Okay, now it turns out that the previous example can be solved by using another method. I wouldn't say method, another approach. So let's take a look here. The first approach, we work on x variable. Second approach, we work on y variable. Now let's take a look at the third approach. Same thing and same line. Okay, now we want this. And we know that from the information we had before, this is 0, this is 2, and this is 4. So we are going to do something different here. So we want this area, but then by the look of this, you notice that, hey, we have this triangle right here. So what about I do this? What about I integrate all the way through, so that in this way I can work on the x variable easily. So in this case, we have this this whole area. Let's take a look here. This whole area, the upper function is this, right? Upper function fx equal to what? Square root of y. And this whole area, let me highlight everything here. This whole area, when you look at the whole area, there is just one lower function right here. That is the x-axis. What about I integrate all the way through everything, and then I just need to subtract that region, that area, with this triangle. So this requires one integration, but then you just use some trick on geometry to work on this to make it easier. So let's find the black area first, the whole thing. Consider everything here. So this black area is going to correspond to the integration starting from x equal to 0 and ends at x equal to 4. Upper function is square root of y. Oh, sorry, it's supposed to be square root of x. This is what happens when you switch things around between two variables. It happens sometimes, but you have to be aware of that. Square root of x, and this is square root of x. Alright, and the lower function is this x-axis, so minus 0 and dx. So this is the whole, the area of this, the black area. But then we don't want the black area. We want to get rid some of them. So we want to get rid of this triangle. So it has to be minus right here of the area of this triangle. So 1 over 2 times the base, that is 2, times the height. Alright, so after this, just do the computation. This is easy. X to the power of 3 over 2, 2 over 3 right here, 0, 4, minus, this cancel, and we have 2 right here. So in the end, we have this equal to 16 over 3 minus 2 equal to 10 over 3. Just like the two ways that we did before. The first way, integrate on x variable, we get 10 over 3. The second approach, we work on y variable, we get 10 over 3. And the last approach, we work on the x variable, but we add geometry trick into that, and we get 10 over 3. So you can see that all these approaches work, but some of them are more convenient than the other. But it doesn't mean that certain approach is better than the other. It depends on the shape of the region you are working on. All right, so keep in mind that the best approach depends on the shape of the region. Do not assume x variable to be easier. Sometimes y is better, and sometimes x is better. Or sometimes you can add some trick like geometry into that to make it even easier. So it's all up to you when you see the shape and you determine which approach to follow. Okay? Now, let's take a look at a few more examples. I want you to see more examples in order to get some experience on this. Now, let's take a look at this one. Here, I want you to find the area of this enclosed region. So we have two functions here. The first one is y equal to cube root of x, and another one is y equal to square root of x. In this case, I want you to work on the x variable. X variable means that you have to use this formula, integration on the x variable, and in this case we need gx here, dx, x start at a, ends at b. With this formula, you need to remind yourself that fx has to be upper, gx has to be lower function. So you have to go back to the graph and take a look at the region and determine the upper and lower. From this region, you can see that the upper part of this region is this line, right? It's at the top of this region, which means that this is going to be equal to fx. What about the lower part? Obviously, this is the base of this region. So it's the square root of x. So this lower part is this square root of x. That is gx. Now that you know the right order of fx and gx, you can continue with the integration. Now integrate. Fx is cube root and gx is square root dx. Starting point on x-axis, that is 0, and ends at x equal to 1. 0 and 1. Now continue with this. This is not hard, so we just integrate that. X to the power of 1 over 3 becomes 4 over 3. We have to divide by 4 over 3. It becomes 3 over 4. This becomes x to the power of 3 over 2, and you have to have 2 over 3 right here. Evaluate this at 0 and 1. So in the end, it comes out to be 3 over 4 minus 2 over 3. Minus 0 goes in, everything becomes 0 here. So in the end, you have this 1 over 12 as the final answer. Okay, and in this case, we work on the x variable. Right? Now, let's work on this differently. In this time, we want to try to use the y variable instead. So y variable this time. Let's take a look here. Y variable. We have this y equal to as the cube root of 3 as the first curve. And another one is this y equal to square root of x. All right, we have two of these. And we need to use the formula that is modified to work on the y variable. So in this formula, we have this area equal to integrate of fy minus gy. Perform integration on y variable, starting at y equal to c, ends at y equal to d. And you need to know that fy right here has to be the right-hand side curve, and gy has to be the left-hand side curve. Now you have to come back to this same region, but you have to look at this differently. We have this region, just like before. Before we can see that one is lower, one is upper. But in this case, we want to look at this horizontally. In this case, you can see that the one on the right-hand side is this. The one on the right-hand side of this region, all the way through, is this. So this square root of x, right-hand side, and the one on the left-hand side of this region is this line. So we have this on the left-hand side. But then, in order to use this formula, we cannot just use this function that we had before directly, because this is expressed as the function of x. So we have to do some moving things around. So we are going to make that line to be a function of y. So this becomes x equal to y cubed, and this, after moving things around, you have x equal to y squared. And with this, you can assign this one to be fy, and this y cubed to be gy, because it's on the left-hand side. So let's put everything in the formula. Fy is y squared. Gy is y cubed dy. Now, what about the starting point c and d? We have to take a look at the range on the y-axis. The whole range is this. So starts at 0 and it ends at 1. Starts at 0 and ends at 1. After that, just integrate this normally. This becomes y cubed over 3 minus y to the 4th divided by 4. Evaluate at 0 and 1. So here we have 1 over 3 minus 1 over 4. Minus 0 goes in, everything becomes 0. And in the end, you have 1 over 12, just like before. So it's the same area. The result should be the same, right? Here we have 1 over 12, and same here. Why do I have to show this? I want to show that in some case, you can pick either ways. Because sometimes you can see the lower and the upper function on the same region, but in the different direction, but in different direction you can see them as on the right and on the left. It's just how you interpret this region, whether you have base and the top, or the right boundary and the left boundary. It's just how you see it. All right. So it's important that you look at the shape and you determine which one to work on, which approach to work on. Now, let's take a look at some examples here, and you'll see what I mean when it comes to determining whether I should go with X or should I go with Y, which one is better. All right. So the best way is to plot the graph, look at the region, and determine. Now we have two examples here. We are going to determine whether we want to work on X variable or Y variable. For X variable, we look for upper and lower function, and for Y variable, we look for right and left. Now, let's take a look at this one. So here we have some region here, and let's take a look at the first region. This region is trapped by two curves. The first one is this red line. And this red line is y equal to 2x squared. And then we have this blue line right here. And this blue line is y equal to x to the fourth and minus 2x squared. The question is, do you see upper and lower or right and left? I give you some time. All right, do you see upper or lower? Upper, lower, or right and left? To me, it's quite obvious that I have one line at the upper part of this region. Look at this red line. It's obvious that all the way through from minus 2 to 2, this line is the upper part of this region. Right? And the blue line is obviously the base of this region. So I see upper curve and the lower curve, so I decide right away I need to work on X variable. Okay, so in this case, it's going to be better if you work with the X variable. In this case, it's going to be integration of the upper curve, which is the 2x squared, minus the lower curve, that is x fourth, minus 2x squared. And we integrate this on the x-axis. Okay, and the starting point and the end points for the x variable is this minus 2 and 2. Minus 2 and 2. I'm not going to go through with this this computation right here. You can do this on your own. This is about determining which to go for, x or y. Now you ask me, can I choose y? Yes, you can, but it's going to be a little bit more complicated. Maybe not a little bit. It's going to be much harder to use the y variable. Let's take a look why. So, in order to use y variable, you gotta have the right and the left boundary for the region you have. So let's take a look at the first section of this region. Here you can see that this is the left, right? This is left boundary. And what about this is the right boundary. And then, okay, I need to get things together. This is getting quite long, right? The green line is the right boundary. What about the left? It's going to be this. Okay, now that is the first section of this region. But then you don't include the region down here, and you can see that region down here has different right boundary. The right boundary here is blue, and the left boundary here is also blue. So it's going to be very tricky to work on this part. Same thing here. Right boundary is here, left boundary is here, same blue line. Right? And after that, you have to work on this last section. In this section, the right boundary is blue, and the left boundary is this red. Everything is different here among all 4 sections. So it's not going to make sense to go with y variable here when x is obviously much more convenient and easier to solve. One line for upper and one line for lower. All right. Now let's continue with one more. All right. We have this region. We want to determine whether we should use the x variable or y variable. Now looking at this, it's quite obvious to me that we have this boundary on the right hand side of this region, and then I have this boundary on the left hand side of this region. So from this I see left and right. That's what I see from the graph, which means that I want to work on the y variable. So let's put the formula in here. So we have this area. In this case, we want to work on this formula, fy minus gy. Work on the y variable, c to d. Now, fy is the one on the right hand side. That's going to be this. It's going to be 12y squared minus 12y cubed minus g of y. So it's going to be the one on the left hand side. It's going to be that. So 2y squared minus 2y. And we work on the y variable. What about the end point and the starting point of this integration? So you can see that in terms of the range of y, it spans from 0 to 1. 0 to 1. Okay? So in this case, it should be better. It would be much better to work on the y variable. Okay. Now, that is how you determine which approach to follow. Let's take a look at the last one for this lecture. So we have this shape that we want to find the area. We have this shape. So in this shape, it's enclosed by 3 lines. The first line is this straight line, y equal to x. Next line is this y equal to x squared over 4. And the last one is x equal to 1. So this region is created from 3 lines. Now the question is, which one to go for, x or y? Well, in this case you can go either way, but to me, looking at this, I see right away that this line is on the right hand side and this line is on the left hand side. I see right and left, I pick y variable. Okay, so I'm gonna need this formula from c to d, fy minus gy. Integrate on y variable. Now I need to determine fy and gy. Fy on the right, gy on the left. So this must correspond to fy on the right, and gy, this straight line from the left. So I need to do some switching of the variable. Y equal to x, y equal to x squared over 4. Need to switch this to become function of y. So this becomes x equal to y, and this becomes x equal to 2 square root of y. And this is f, oh, no, this is gy, and this one is on the right, so this is f of y. Now I go back to the formula. I need to integrate this fy, which is 2 square root of y, minus gy equal to y with respect to y. What about the range? I look at this. Range of y spans from 0 to 1. So put 0 and 1 right here. So this becomes 2y to the power of 3 over 2. And then I have to have this 2 over 3 right here. Alright. And then this becomes y squared over 2. And we need to evaluate this at 0 and 1. So in the end, we have this 2 over 3 minus 1 over 2 minus 0 goes in, everything becomes 0. So I have this equal to 5 over 6. So if you pick the right variable to work on, this can be solved quite quickly. On the other hand, if you choose to work on the upper and lower, it means that you have to split this region into two parts, because if you work on x variable, upper and lower, you can see that there is one lower that is clear, right? One lower line. But then on the upper part, you have two of them. One line right here and one line right here. So if you worked on the x variable, upper and lower, you need to work on two integrations. So in this case, I recommend you use the y variable to find the area. And this is the end of this lecture.